So last time we talked about the difference between static and kinetic friction data-wise. So we used a PhET, and you kind of cranked out a bunch of different things, and you were able to find mu static and then mu kinetic, and kind of just knew a couple of properties. But it wasn't great because you couldn't do something directly in front of. So today I kind of want to spend a little bit of time doing that. Describe the difference between static and kinetic, kind of do different types of problems with it, and then hopefully do more practical things with it. So here's what I normally would do. I'll give you kind of a wooden box in your groups, a spring scale, and then 200 grams. So the spring scale is just a way to measure how much force, and it's also a way to measure how much weight something is. So remember, weight is a force, but normally when we have objects that are weighed, we get the mass. But the spring scale gave both a mass and a force, but the mass is pretty much just divided by 10, which is the acceleration of gravity. So the spring scale is going to do two things: tell us how much force applied it's going to have, and also we could weigh our box. The box actually weighs 800 grams. That's why I add the 200 grams just to make life a little bit easier. So the total mass is 1 kilogram, which is nice because then Fg is -10, and then force normal is +10. So right now we're going to just set this aside. We know those are the values, but right now I really want to focus on what's the difference between static and kinetic. So what I'll ask you to do in class is to pull this box perfectly horizontal. So we're going to add, let me go back, I accidentally changed it. So we're going to pull at a force perfectly horizontal, and we want to keep pulling until we see something. Pull until it moves. And we want to see what's going to happen. So if I show you this video, it's really quick. And thank you whoever uploaded this, Mr. Richard Walding. So it's a really simple but detailed video. So if you watch right now, it's at 0. This is a spring scale. It's at 0, and you're going to watch the force going to increase over time as they start pulling. So right now it's 0, not pulling at all, and all of a sudden it's going to increase. Notice it's increasing, but there's no motion. That's why this is going to be called static friction. So you're going to increase, and it's going to keep increasing, still no motion. It's going to keep increasing until it starts to move. So that's the key there. So in this way, what's it going to do is it can go from 0 to its max, and then starts to move. Okay. Now, the significance of it is my next page. So what is this? This is called static friction. And this is force of friction when it's not moving. And that's why it's called static. But it's very important. Okay, direction is going to be the opposite direction of the force. So force applied is to the right, then force of static friction is going to be to the left, and the magnitude is going to be 0 to its max. So if I'm pulling with +1 newtons, then force of static friction is going to pull back -1 newtons. And it can keep going until it starts moving. So kind of like that video, you'll see it getting bigger and bigger and bigger. So I'll have this done on a table, and then I'll ask the same thing on a piece of paper, and then you're going to tell me the difference. Now, if it's on a different surface, it's going to have a different force. And the reason is because of how rough or smooth something is. So even though something looks smooth, a piece of paper is pretty smooth, our tables are pretty smooth, in reality there's a lot of little rough edges between the two, and this object has to overcome these ridges. Another way of kind of explaining is kind of your knuckle. So if you put your knuckles together and then you try to go over it, it's going to kind of rub and not feel pleasant. So when an object is sliding, they have to make it over these bumps. So a smooth surface, it doesn't. The rougher surface, it's going to get more and more. Now you'll notice back to this slide back here, I made it so that our Fn and Fg were nice numbers. And it might seem weird, like why do you even care? we're pulling to the right or left, and friction is also to the right or left, so why do we care about the up and down motions? And in most cases, actually all cases except for friction, if they're in different axes or different planes, the forces don't affect one another. And the only exception is friction. And this is why. As this thing is moving across, notice that my hand has to go up and over the bumps. So that's when Fn actually becomes relevant. So if something's lighter, it's going to take less force to go over something compared to something heavier. So if something's heavier, then it's going to have a bigger Fn, which then it's going to take more effort to go over. So Fn is actually really important. So if something's light, it's going to be less friction. Something's heavier, it's going to have a little bit more friction. Now, here are the equations for static friction. So you're going to have force of static friction is equal to mu s over Fn. And then force of kinetic, it's almost the same thing, but instead of mu s, it's going to be mu k. Now, before we get back to that, I do want to show that it's going to be different. So if we're sliding, the number is going to be different. And I'll kind of show you back to this one. So kind of watch what's going on. So it's at 0. It's going to increase, 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 increase. And now it's kind of between, it was, I think, 2 and 3 newtons. And then it starts moving. But notice it's right here, right now, between 2 and 3. But as it keeps moving, look what happens to the scale. It goes back down to 2. So it goes all the way up to 2.5, starts moving, and once it's moving, it jumps back down to 2. Let's watch that again, just so you know that I'm not lying to you. So 0, 1, 2, 3, and watch where it goes. So when it starts moving, it's like between 2 and 3 before it moves. It moves at 2.5, and then it jumps back to 2. So what's going on? And that's kind of what I wanted you to get from the PhET, that it takes a little bit more force to get something to move, but once something's moving, it's going to require less force in order to keep it in the same constant velocity. So force of static friction is always going to be bigger than force of kinetic friction. So when we're looking at that equation again, let me go ahead and go back. Even though they're both the same equations, here you have force of kinetic friction is mu k over Fn, and here's force of static mu s over Fn. Mu s is always greater than mu k, and they're always between 0 and 1. This is most friction, and this is no friction. Okay, and it can't be over 1. And the reason is because if friction is bigger than 1, that means the amount of force to push it forward or backwards is more than it weighs, which technically can't happen because then you can just pick it up and just move, right? So it has to be at least equal to. Now, the only exception is something like Velcro, but that's no longer friction. It's actually a hook into a loop and it's holding on. So you have to think of it more like glue than it is friction. So friction mu is always between 0 and 1, and this applies for both static and kinetic. Static will always be bigger than kinetic. So as long as you keep that in your head, you'll be totally fine. Okay, so the properties from the PhET is that you have this equation. We were able to kind of graph it, and we were able to find y and x. And this was the m, or the slope. And we noticed that mu s was always bigger than mu k. So the amount of force required to start it up is always going to be less than it is to move it. Okay, so those are the big ideas from last week, and I wanted to emphasize it more today. Now, kind of go back. So here's kind of example of what's going on. You have force gravity, force normal, force applied, force of friction, and depending on what it is will determine what kind of friction it is, whether it's kinetic or static. Now, we're going to do some sample problems, and I pretty much want you to kind of go through this. Okay, draw a free body diagram to say what's going on. Ask yourself if this thing is moving or not. Okay, so if it's not moving yet, then you need to figure out whether it's going to move at all. Once it's moving, then you're going to do find the acceleration. So it's kind of like something I always want you to go through and just kind of think it out what's going to go happen. So here's our first example. So what's the acceleration of the box if a person pushes it with 50 newtons and the initial velocity is 0, mu s is 0.6 and mu k is 0.3. So the main goal is to figure out it's A, acceleration. So we're going to have force applied, force of friction, and then we're going to use this equation. Sum of all forces is equal to force applied plus force of friction equals ma. And our goal is to find that A. Okay. The problem is we have no idea what kind of friction this is, right? Is this static or is this kinetic? If it's static, it's easy. It's not moving, right? Because static only works if it's not moving. So we don't know if it's kinetic or static. Okay, so let's find out. So it starts at rest, so we have to figure out whether it moves or not. So we're going to have to find Fn. So force of static friction. Static friction is equal to mu s Fn. Okay, so we need to figure this stuff. We already know mu s, so 0.6, but we do need to know Fn. So gravity is pulling down. This is 10 kilograms. Gravity is pulling down with a force of gravity of negative 100. That means force normal is pushing up 100 newtons. Plug that in, and you get 60 newtons is the force static friction max. There's the key right there, max. It could go from 0 to 60. Now, if the kid's only pushing 50, is that greater than 60? And the answer is no. The force applied is less than force of static friction max. So that means, therefore, acceleration equals 0. That means velocity is 0. Okay, so this is what's going to happen. Okay, now let's do the same thing, but this time, let's say the kid now pushes with 80. So if he pushes with 80, so it's the same exact problem. So force of static friction is still the same. It's still a 10 kilogram box. You still have mu, same numbers. But now, instead of less than, force applied is greater than, because it's 80 this time. So we know force applied is 80, and we still want to look for ma, but force of friction is not 60. It's not even negative 60. And the reason is because this is force of static friction. What you need now is to calculate force of kinetic friction, which is the same formula, but instead of using 0.6, you're going to use 0.3 times the same number, 100. So in this case, you're going to use not 60, but 30. So you have to be careful there. Once it's in motion, you totally ignore force of static friction. So then you have 50 equals ma. The mass is 10, so 50 equals 10 times a. So a is equal to 5 meters per second squared. Okay, so that's how you do it. Okay, I'd like you to practice this, and then we'll kind of work on it in the class together. But hopefully that makes sense.